this assignment, we're doing some mixed practice with derivatives. Our first problem is not a derivative. It is just a question of, do you remember what your inverse tangent function looks like? Remember, we fold across the 45-degree line, so our vertical asymptotes become horizontal asymptotes. So our limit, as the angle goes to negative infinity, we're working in this area of the graph. So as our angle, our x-coordinate is theta here, our independent variable. As it goes to negative infinity, we're getting closer and closer to the the horizontal asymptote of negative pi over 2. All right, now we're practicing our inverse trig derivatives. So this is our glob here of u, so don't forget the chain rule. The derivative of inverse sine is 1 over the square root of 1 minus that glob squared, and then we need to do a chain rule on that 2x glob, so that would be a 2. And number 3, derivative of arc cosine or inverse cosine, almost the same thing, but we have a negative, and then we have the square root of 1 minus our glob squared this time would be a 9x squared, and then our chain rule on the glob would be a 3. So you don't need to do these in 2 steps if you're thinking 1 step ahead of the game. You could, of course, put the chain rule in the numerator right away. All right, now we've got a composite function. We're doing the arctangent of a cosine. So this glob, cosine x, takes the place of the angle inside the arctangent function. So the formula for the derivative of arctangent on the outside is 1 over 1 plus the glob squared. So this time the glob squared is cosine x, and then times our du dx chain rule. So the derivative of cosine x is negative sine x. So we could rewrite this. And if this were a 1 minus cosine squared, that would be a Pythagorean identity, but it's a 1 plus cosine squared, so I don't think we can really make this look much simpler. All right. Now we're going back to practice some implicit differentiation. Remember, when it's not solved explicitly, y equals is an explicit function. So we're doing implicit, and here's the result we want to come up with. So our operator is d dx on each side. So we want to take the derivative with respect to x on each side of that equation. And you need not write this first step, but it might be good to stop and think of your plan. On this term, we're going to need a product rule. So it's actually going to stretch out to 3 terms on the left side. And check every time you do a derivative on the y term, remember to add a chain rule. So when we do the derivative of our first term, we'll do the power rule first, 6y to the first, and then times the chain rule. You can write y prime if you prefer, or dy dx. And then for our product rule, you can keep the 2 with one of the terms, or you can put the 2 outside the product rule. That would be your choice. So I'm going to do the first term, leave it alone, times the derivative of the second term. The derivative of y is just 1, with then a chain rule on the variable. And then plus our second term, y, times u prime. The derivative of x is just 1. No chain rule needed on the x variable. And on the other side, the derivative of the 4x term is 4. Again, no chain rule needed on x. And the derivative of the negative 1 is, of course, 0. So we would like to solve this. Our directions said to find dy dx. So if I rewrite this a little bit and keep the 2 terms that have the dy dx on this side. So notice this 2 has to be distributed. So if I keep these dy dx terms here, but if I move the 2y to the other side right away, and then we're going to factor. And actually maybe this might be a good reminder that everything here is divisible by 2, so you might take care of that first, or of course you can factor and cancel later. So just remember to look when you're treating equations whether there's a common factor all the way through. So now if I factor the dy dx as a GCF, I would have a 3y plus x. So I'm going to divide that to the other side. And that should be our best answer for the derivative. In number 6, we've seen this before. Here's a product rule, and inside there could be a chain rule. Notice that this glob x plus 3 does not need a chain rule because its inner derivative is just 1. This parenthesis will require a chain rule because its derivative is 2. All right, so let me set up our product rule. So we're going to take the first and leave it alone, times the derivative of the second requires a power rule on the glob, and then a chain rule on the inner glob. And then plus our second function, leave it alone, times the derivative of the first function requires a product rule. And that would be reduced to a 4. And then just to make our point extra clear here, the chain rule would just be a 1. So always safer to double check to see when you need that. All right, so now when we do this, let me just clean up each of these terms here to make this a little more visible. Many of you would be prepared to go right to the next step where we're going to factor the GCF. But if I write these terms in similar order here, just commuting those terms. So here our coefficients of 14 and 5 do not have a GCF, but of course we've reduced the power of each of these terms by 1. So our GCF will be an x plus 3 to the 4th from each part, and a 2x plus 1 to the 6th from each part. So this is our GCF. And now from the first term we still have that 14 left, and we have one of the x plus 3 parentheses. And we have from the next part the 5 left, and there we have one of the 2x plus 1 binomials. And don't quit. That has like terms, so let's clean that up. So we've got a 14x plus a 10x, so a 24x, and 14 times 3 is 42, plus a 5, so we have a 47. And sometimes you'll remember that this term might have another GCF that we might want to bring on the outside, but I do not believe that 24 and 47 have a GCF, so I think that would be our final derivative form. All right. Question 7. The logarithm of a glob. So we're asked to find dy dx. I might, just for sake of reminding you that you can use either notation, I might write this as y prime. The derivative of the natural log is 1 over that glob. And then we need to do a chain rule on that glob, so a 6x. And every time you do this, aren't you expecting some things to cancel? So that will become a 2. We can cancel the x, so we'd still have an x. So it looks like we have a 2 in the numerator and an x in the denominator. And here, be careful, this is not in number 8, this is not a product rule. Sign requires an argument. So this is the sign of the natural log of x. This is not a product rule. This is a chain rule. This is one function. inside the argument of the sine function. So I'm going to do the derivative of the outer function first, and then the chain rule, the derivative of the inner function. So our derivative would be the derivative of sine is cosine, leave the glob alone, times the derivative of the inner glob would be 1 over x. So however you want to write that, but notice that this is not cosine all by itself. This is the cosine of the natural log of x. And that would be our simplest derivative there. Now let's compare that to number 9. Number 9 is very different because here we have sine of x, that is a complete function, times the natural log of 5x. So this one is a product rule because we have one entire term times another entire term. So our derivative, the derivative of y, you could write as dy dx or a y prime. So on the product rule, I'm going to have the first function times the derivative of the second is 1 over 5x times the chain rule would be a 5. So those 5's are going to cancel. So this is our u v prime from our product rule. And now we've got to do v times u prime. The derivative of sine x is cosine x. And I don't really see anything that simplifies there. So we have sine x over x plus, and now these two terms, I don't think there's one order is any better than the other. So that is, I think, the best we can do there. This might look familiar when you see sine x over x. That is not equal to 1 because it doesn't have a limit on it. Remember, we had a theorem that said the limit as x goes to 0 of that value, that would be equal to 1. But this does not have a limit on it, so it is not the same as our limit theorem. All right, in number 10, find g prime of x if we are given that g is the natural log of this product rule. So think about what we have here. This is definitely a composite function. So the natural log has a function inside it, and the function inside it happens to require a product rule. So let's maybe analyze this a little bit more. So we've got the natural log, and then inside that natural log we have an x term times an x squared minus 1 to the 1/2 power. So it's going to take a little bit of thinking when we do this product rule because our v term itself is going to have another chain rule. So chain rules inside of derivatives, be very careful to make sure that you do every required chain rule. So to find the derivative of this composite function, first I do the derivative of the outer function. So the derivative of natural log is 1 over the glob. So let's just leave that glob alone. And you can put the square root symbol back if you prefer that. So 1 over the glob is the derivative of natural log of the glob. But now we've got to do our chain rule. And our chain rule here is a product rule. So we're going to have u function, let's leave x all by itself, times v prime. So let me maybe see if I can, without slowing us down too much, our u function I'll do in blue, and then times our v prime is going to require our power rule, 1/2 the glob to the negative 1/2. And we're not done yet because that has a derivative, a chain rule inside of 2x. So there's our v prime term. And then to finish our product rule, we're going to do the v term. So leave it alone, x squared minus 1 to the 1/2. Times u prime. So let me scroll a little bit here. We're need quite a bit of space. The derivative of u is just 1. No chain rule required on that. All right, so it looks like we've got quite a mess here to clean up. Let's see what the best way of writing this is. If in doubt, write them all in the same form. So I might want to get rid of those negative square roots. So let's see if we like it better if we put these each in square root form. So here I've got an x times a 2x, so let's put 2x squared in the numerator. And then we've got this 1/2, and this glob is to the negative 1/2 power, so let's move it down here. And then we've got to take our second term here, and that looks like the square root of x squared minus 1. All right, so we got to think of what can we do easily to clean this up? Well, I got one step I see right off the bat. How about if we cancel those 2's? And I see another step here that might not be clear because I missed exactly what I tell you guys not to miss. So this multiplication, this first fraction is times the entire chain rule. So let's get that very clear. And so I can think of this as distributive property, and I think that cleans up kind of nicely. When I multiply these first two terms, this x in the denominator will cancel with one of these terms. And look at the denominator, the square root times the square root will just become x squared minus 1. And not so bad when we multiply our outside fraction times the second term, that radical cancels out, and it looks like we get a 1/x. So the question now might be, do you need to get a common denominator to put those together? And we're not exactly sure if that would serve any purpose, so I think this answer might suffice. If you want to proceed to get a common denominator, we would multiply the first fraction up and down by x, and we would multiply the second fraction top and bottom by x squared minus 1. So now we have a common denominator. So if we add these together, we've got 2x squared minus 1 over x times the quantity x squared minus 1. The numerator doesn't factor, so I don't think that really did much for us. So when in doubt, if you're not sure if you have time to try more algebra, leave it in its previous form. All right, let's see if we can finish up here with 2 more. Here we have the natural log of a sum. So h prime of x is the derivative of the outer function. The derivative of natural log is 1 over the glob. And we might be able to clean that up by factoring. Maybe you might want to factor first. So the derivative of a natural log is 1 over the glob, and then times the chain rule on the glob. So the chain rule, the derivative of the first term, the derivative of e to the x is, or to e to the glob is e to the glob, times the chain rule on the glob would put a -1 as a chain rule. And this second part, we're just having lots of fun here. This is a product. This is an x times or a u times a v, where our u function is x and our v function is e to the -x. So let's stretch it out here and let's be careful we don't miss anything. So we want our u function times our v prime, we just did that, plus our v function, leave it alone, times our u prime, the derivative of x is just 1. So that chain rule had a product rule mixed in with it. All right, so now let's see what we can do here. We've got 3 separate terms, but each one of them has an e to the -x. as does in this denominator, as this denominator also has a common term of e to the negative x. So I think we might want to get those factored out. And the question is whether we want to factor out a negative sign here. That would be up to you. Let's just factor out the e to the negative x, and then let's see what terms we would have. We would have a negative 1, and then we would have a negative x, and then we would have a positive 1. So these two terms are going to cancel each other out. And let's see what we've got at this point. You could start canceling, but let's make sure we're all together on this. I'm not sure I did the easiest order. I might have done some of that factoring earlier is the question or the decision, but now we can see that those two cancel out. Wow, that was a lot of work to come up with an answer of negative x over 1 plus x. Okay, so let's just take a quick look back at the original. Do you see that perhaps you would like to put this in factored form before we started? I don't know if it would have made the algebra simpler, but it might be worth a try. All right, and one last problem here. We have a large, oh, it's not a derivative. I was going to do a quotient rule, but look at here, we're only asked to do the limit. So we want to practice our theorems, the two special theorems with cosine of x minus 1 over the value of x. So let's split this up using our limit laws. And you have to come up with, you have to be pretty good at seeing one step ahead of where you're working. If I keep the first two terms together, but factor a 5 out of that, and then I have to write that over 3x, and then the second part. So I'm not really doing anything yet, but I'm splitting it up so that this is getting close to our limit theorem with cosine x minus 1, and this is getting close to our limit theorem with sine of a glob over the glob. So now we just have to take care of these constants. So in this case, we can bring the constant out in front, and then it will look exactly like the theorem that we know. And this next one, remember the 7x here, we can't get that 7 out of the sine value, but we can bring the 1/3 out of the limit. So we're getting very close to what we want. Sine of 7x over now just x, and we need a 7 down there. To apply the theorem, we need it to be the sine of 7x over 7x. So how can I put a 7 in the denominator if I multiply the numerator by 7? So we'll just cheat and put it right there. All right, so what do we know? This theorem goes to 0. So 5/3 times 0, of course, is 0. This theorem goes to 1, so that would be 7/3. So there's our answer for our last problem.